Okay. Okay, maybe we can start. Good evening, everybody. Today we have a pleasure to have a talk by Frank Sauressig. He will tell us about asymptotic safety and friends. Please, 1 hour.
Thank you. So it's a great pleasure to give this talk. So I also want to thank the organizers to giving me the opportunity to give this introduction to asymptotic safety and explain its relatives. So then there's a little bit of advertising here. So if you want to learn more about the topic, there's the textbook by Martin Reuter and myself. So this is much more detailed. So during the talk, we only touch the tip of the iceberg. Then I am very happy to be interrupted during the talk. So if there are questions coming up, don't hesitate to ask. Also, I should put up a warning sign. So I'm broadcasting out of the home office. That means I'm sharing the home office with kids. And by now they have developed the curiosity for quantum gravity. So if someone shows up, just be patient. Typically they get bored within a minute or two, and then they also leave again. So this brings to the outline of the talk. So I want to start with motivating why doing quantum gravity research is a very timely subject at the moment. Then I have 3 introductory chapters about asymptotic safety. So I want to outline the basic idea. I want to explain the computational toolbox that is frequently used to actually explore the scenario. And then I will give a brief example how to put this toolbox into practice. Then I will deviate a little bit and talk about modern developments in the program. And there I opted to talk about form factors because this is a natural overlap with the non-local quantum gravity community for the seminar series. And if time permits, I want to go to an outlook and give a long-term vision for a common program. So this said, let's get started. So let's go for motivation. So the starting point for describing gravity is general relativity. So we know in this case, space-time becomes a dynamical object. The dynamics is described by Einstein's equations, and they are written here. So on the left-hand side, we have the curvature of space-time, we have a cosmological constant, and on the right-hand side, there's the matter populating our space-time. So if we have matter, it tells us how space-time should be curved, and the curvature tells the space-time how to move, the matter how to move. And the equation that we have up here is experimentally extremely well tested. So there's a whole set of traditional tests that have been performed in order to verify the validity of these equations. So gravitational redshift experiments, bending of light experiments, all have been successfully described by this framework. But then in the last couple of years, there are also new classes of experiments coming up, the detection of gravitational waves and shadow imaging. So these essentially allow for a new class of tests of these equations. Essentially, they allow us to probe regimes where gravity is actually strong. So this is in contrast to the traditional tests where you have gravity as a weak force. So we can enter a new regime. So this gives some motivation to actually get predictions for these new observational regimes. Then there's the natural question, why do we believe that there's something new that could happen in these areas? And the first motivation comes from solutions of general relativity. So a very common feature of these solutions are space-time singularities. So if we write down the Schwarzschild metric, we see that the structure is as follows. So we have an external space-time, which is asymptotically flat. then we have an event horizon, and below the event horizon, we actually have a curvature singularity. While this is the prototypical example that we teach for bachelor students, this is a rather generic situation. So singularities are common in general relativity, and it's commonly phrased that at these points, general relativity predicts its own breakdown. Now, we can also move in the direction of particle physics and see what happens if we want to describe particle scattering in the framework of general relativity. Let's construct a prototypical example. Let's take the Einstein-Hilbert action. So this is this part, just in flat space, the curvature tensor here, and couple it minimally to two scalar fields. So phi and chi is minimally coupled to the metric. Now, we can ask for a scattering process mediated by gravity, where two phi fields go to two chi fields. We can do this in a Minkowski background. So then we have to evaluate one Feynman diagram that is depicted here. So the dashed lines and the straight lines are the phi and the chi fields. And there is a graviton which is exchanged between the two. Now, since this is a 2-to-2 scattering process, we can introduce Mandelstam variables to describe the corresponding amplitude. And the important one is S, so this is the center of mass. Now we can take the action that we have up here. We can compute the propagators and interaction vertices entering into the diagram. And then we can compute this amplitude. So it's proportional to Newton's constant and a combination of these Mandelstam variables. So if we go to the limit where we have a large center of mass, this reduces to the combination Newton's coupling times S. So this can easily be seen. The amplitude itself is dimensionless. The Newton's coupling has a mass dimension of -2, which needs to be compensated by 2 powers of the center of mass energy. Now, if we extrapolate this process to scales where the center of mass energy becomes comparable to the Planck scale, then we see that the right-hand side here grows without bound. So we have a problem of the amplitude staying bounded. Then one can ask, okay, this was a tree-level computation. What about loops? And the basic effect of adding loops to this correction is that they aggravate these divergences. In principle, you can make this argument on dimensional grounds. So higher loop corrections come with higher powers of G, which have to be compensated by higher powers of S to get to something dimensionless. And from that, we see that the divergence structures does not improve if we compute corrections to such a diagram. Now, there's a third argument that we can field. So this has been done in the 70s. So one can canonically quantize the Einstein-Hilbert action. And then it turns out that there's a non-trivial two-loop divergence coming in this quantization process. So here is the counter term that has been computed in this context. And what we see is structurally, this is not of the form that we have in the initial action. So we cannot absorb this divergence in a redefinition of G. And this is the hallmark that we are actually dealing with a perturbatively non-renormalizable theory. Nevertheless, it's clear that the Einstein-Hilbert action will work as an effective field theory. So in this way, we can still get predictions out of it, which are then limited to energy scales below the Planck scale. So that is well under control. Now, then based on this assessment, we would like to have a theory of gravity that works on all scales. And here is my cartoon version of different ideas that have been fielded in this context. So clearly there is the string theory branch that wants to describe quantum gravity in terms of the gauge gravity correspondence. There's the loop quantum gravity line. There are pre-geometric models which start from very elementary tools and want to derive space-time out of it. And the focus of this talk will be on quantum field theory-based models. So there's asymptotic safety, which already featured in the title. There's the causal dynamical triangulations program. There are the perturbatively renormalizable quantum gravity theories and also non-local gravity theories. So they all follow in this branch. I will have nothing to say about the other ones, so the focus will be on this green thing. Now, let's go into the region of asymptotic safety and explain the basic idea. So let me repeat, if there's something unclear, feel free to ask questions in this process. So let's start by defining the arena in which asymptotic safety is placed. So first, we want to state the input. And as an input, we specify two things. We specify the field content of our theory. This is taken to be the space-time metric g mu nu. So this carries the gravitational degrees of freedom. And then we also specify symmetries. And here we copy the symmetry group of the Einstein-Hilbert action. So we declare we want to have invariance under coordinate transformations. If we have this input, we can start constructing actions. So in principle, an action is built from the field content that we introduced up here, and it should be compatible with symmetries. The prototypical example is the Einstein-Hilbert action that we already had in the introduction. Now, if we have all possible actions that we can construct in this way, we combine them into a formal object. So this is called the theory space. So by definition, this contains all actions which we can construct from the fields and which are compatible with symmetries. Then it's convenient to introduce coordinates on the theory space. So these are the coupling constants that typically appear in our theory. And then it turns out that the theory space contains an additional structure. This is the Wilsonian renormalization group. So essentially, this is a vector field on our space, which tells us how coupling constants change if we integrate out quantum fluctuations. Now we can summarize the structure that we have here in a nice cartoon. So the object that this talk is played on is the theory space. It's spanned by action functionals constructed from metric. It contains a vector field. This is the vector field associated with the renormalization group. We can construct integral curves of this vector field. So these integral curves are called renormalization group trajectories. And what we are interested in are complete trajectories, which extrapolate from high energies, the bare action, to the effective action once all quantum fluctuations are integrated out. Now, if we take this arena, then one could notice that as asymptotic safety is not the only quantum gravity program that actually lives on this space. So if we say we are dealing with action functions constructed from the metric, then there is a whole set of quantum gravity approaches that will live on this space. Asymptotic safety being one of them, non-local ghost-free gravity as well, quadratic gravity, and super-renormalizable gravity theories. They will all live on this space. Let me then also give an example of a theory that is not in this space. So here one could think about Horava-Lifshitz gravity. This fails to be in this space because it doesn't share the symmetry group that we imposed on our action functionals A. Now, what makes asymptotic safety asymptotic safety? So what we are interested in is finding well-defined high-energy completions of our RG trajectories. the way to do this is we want to have a randomization group fixed point which controls the theory at high energy. So the typical structure that we have in mind is depicted on the graph here. So here we have such a fixed point sitting in the middle. We have constructed randomization group trajectories which go out of this fixed point. So all the arrows that we see here go to lower energies in the direction of cross-graining. And then we can distinguish essentially two sets of trajectories. So there's one set of trajectories that goes into the fixed point under the inverse RG flow. And then there are trajectories which just go away. And in order to enjoy the benefits of having such a fixed point, we demand that our theory is actually of the first kind. So it should approach this fixed point in the ultraviolet. Now the question, why is this a good thing to have? Let's go back to the amplitude that we constructed before. So we have the amplitude here. We denoted that this is proportional to Newton's coupling and the square of the energy, center of mass energy. And we note that this combination is actually dimensionless. So having a fixed point means that all dimensionless quantities will stay finite. And then we see that in this way, we can actually get rid of precisely the divergences that we find in the canonical quantization or at the tree-level amplitude. Now, it's a question, which fixed point should we actually use? There are multiple choices that we can make. So the fair question is, should we use yours or mine? And at that point, it is quite useful to distinguish between two categories. So we have two types of fixed points that we can use for a UV completion. So there's a Gaussian fixed point, where the corresponding theory is actually the free theory. Now, this is what we typically...
Excuse me, I
Sure.
see that Philip would like to ask a question.
Thank you.
Yes.
A moment ago, you discussed relevant and irrelevant trajectories. How did you conclude that the one that you got for the G times F was relevant rather than irrelevant? Because I'm guessing the irrelevant ones will diverge.
Yes, it's true. So the hypothesis is that all the good things are actually aligned with the relevant directions. So if you would sit on an RG trajectory that is irrelevant, you wouldn't enjoy these good properties that we have here. So it's precisely the idea that you should approach this fixed point in the UV, which makes this product finite. So if you sit on an irrelevant trajectory, this would diverge.
Aren't all the irrelevant trajectories the ones that are destroying renormalizability?
Yes.
So you're basically by fiat saying I'll ignore them.
In terms of, yes, by fiat, I'm only interested in theories that end up in a theory in this fixed point. So I would like to ignore them.
Okay.
So by definition, this is not something that leads to asymptotic freedom or asymptotic safety.
Okay. One very quick further question. I'm sorry to ask so much.
No.
So if I write down a path integral over all the trajectories, what percentage of the path integral trajectories are irrelevant in your language?
And so we are dealing with an infinite dimensional space.
Yes.
And most likely an infinite number of parameters that you get to parameterize this space are associated with irrelevant parameters.
Yeah, that's why I asked. Thank you.
So the relevant ones are really a low number. And in the context of quantum gravity, I would predict that this surface, that is the good one, has probably 3 or 4 free parameters to dial.
Okay.
But this is a very important question, I have to say, because it's linked to the predictive power of the theory. So you want to do something that is better than effective field theory, where all the parameters would actually be constants that you have to measure. And by imposing that the theory is on this UV critical surface, you get an infinite number of predictions between the effective field theory parameters. So that is the magic of the construction. Okay, then we can ask about what fixed points are available. And structurally, we have fixed points corresponding to free theories. So these are called the Gaussian ones. And the prototypical example for such a fixed point would be the one for quadratic gravity. So we are dealing with a theory that is perturbative randomizable, and this reflects in the construction as a Gaussian fixed point. Then we can also have fixed points corresponding to interacting theories. Then we would talk about asymptotic safety or a non-perturbative randomizable field theory. And here the example would be gravity in 2+epsilon dimensions. So then we can find such a fixed point in a controlled way by taking epsilon infinitesimal, and we can see that there's a fixed point branching of the Gaussian one.
I have a small question.
Yes, sure.
Where is this fixed point at? Is it at Planck scale, beyond the Planck scale, or below the Planck scale? So,
can I postpone this question to the example session?
Okay.
So I will explain later.
Okay.
So then, by specifying your quantum gravity program you should specify the corresponding fixed point for the UV completion. And for the asymptotic safety program, you would go for a non-Gaussian fixed point, the so-called Reuter fixed point. So this specifies essentially defines the approach in terms of UV completions. Now, if you want to summarize what you demand for this program to be successful, then you would go for the following. So for asymptotic safety, you want to have the high energy completion based on a specific fixed point, the Reuter fixed point. Then we also discussed with Philip that we want to have a finite dimensional UV critical surface. That is important in order to be able to derive predictions. So essentially, you want to be able to identify the RG trajectory realized in nature with a finite number of measurements. So this is ensured by having this finite dimensional space. Now, if we integrate out all quantum fluctuations, then we would like to have an effective action which is compatible with observations. So at this stage, we have to meet the tests of general relativity. And if you also think about including matter, you have tests of the standard model of particle physics that you can apply to see if you are on the right RG trajectory. And then there's also a set of structural demands that you want to impose. So your theory should resolve space-time singularities, it should be causal, and you can probably think of a lot more on this list. Now, let me also remark that whatever you do in terms of quantum gravity programs, all the items that you have in 2 and 3 probably stay the same. It's only the item 1 and the item 2 that you actually can interchange. Now, let's go for the toolbox. So the idea of this section is to convince you that we are not doing some black magic here, but things that you know from quantum field theory, probably at the level of a textbook. So what we need to do is we want to have a tool which allows us to study RG flows beyond perturbation theory. So we don't rely that we have a small coupling in which we can expand. And then there's a series of so-called functional randomization group equations that can be used in this context. So in terms of age, we are practically dealing with the youngest one, so the Wetterich equation in practical computations. So this is a multi-purpose tool, so we can apply it to scalar field theory, up to quantum gravity, and also to condensed matter systems. So it's nothing that is specific to quantum gravity. Now, the basic idea is that we want to integrate out quantum fluctuations. And we want to do this not in one step, as you would do when evaluating a Feynman diagram. So we do it shell by shell in momentum space. The idea is that we first integrate out the high momentum fluctuations, then we get a new effective description, then we integrate the next shell, and so on and so forth, until we have integrated out all quantum fluctuations and found the corresponding effective action. So in principle, you can start this program by imposing initial conditions at some UV scale, let's call it lambda. But if you have a fixed point available, you can push this UV scale up, and then you can actually talk about the UV completion of your theory. Now, how can we implement this picture in practice? And the first good step is to we go to scalar fields and we recall the definition of the effective action. So we start with a generic action S of our quantum field var phi. This is written down here. We construct the generating function for connected Green's functions. So we get the functional integral, we take the logarithm out of it. Then this gives us a generating function that depends on our source J here. We define the classical field as the expectation value of var phi. And then we perform the Legendre transform of W to get the effective action as the generating function for 1pi correlation functions. Now, what changes if we want to construct the corresponding flow equation? So we add one new ingredient to the construction. So we introduce a scale-dependent mass term in our functional integral. And the only purpose of this term is to give a scale-dependent mass to fluctuations with low momenta. So in this way, you see that the high momentum modes are actually still integrated in this path integral, while the low momentum modes are suppressed by this mass term. Now we can repeat the steps that we had before in terms of taking the modified Legendre transform, and we can take the derivative of this object with respect to k to see how this object changes if we unsuppress some of the modes here in the path integral. This leads to the Wetterich equation, which has this one loop form. So formally, this equation contains the same information as the path integral. We only opted for not doing the path integral in one step. So we do this path integral step by step. So if we have this gamma k, the vertices include all the quantum corrections, form the fields with momenta p squared larger than k. One can check that the right-hand side driving the change of this object is actually peaked at momenta p squared going to k squared. And we have the third property. So if we send k to 0, then our suppression term here will vanish. And then we have integrated out all the quantum fluctuations in our theory. So from this, we see that if we have gamma equal to with argument 0, we recover the standard effective action.
Can you just show us delta k again?
Delta k?
Yes. Let me see. Now, the phi is a function of x in that expression?
This phi here is depending on momentum space. So I Fourier transformed what is in here. You can also write it in position space. So then Rk would be essentially a non-local function, a function of the derivative operator acting on phi in position space.
Oh, okay. So you've added a non-local interaction to the path integral, but
yes,
you've got it with very special measures, so it's nicely suppressed.
Yes.
Thank you.
So if we want to copy this construction in the realm of gravity, then we are facing two problems. So the first one is the fact that our theory should retain invariance under diffeomorphisms. And the second is related to the definition of the Gauss-Kreinig scale. So when I go one slide back, when I introduced the separation of high and low momentum modes, what I secretly used is that I have a Euclidean background metric that allows me to distinguish large p squared from small p squared. If you have a dynamical or fluctuating metric, then it's not so clear what you should do. But you can solve both of the problems at hand here by resorting to a background field method. So essentially you take your dynamical quantum field, you decompose it into a fixed background and fluctuations in this background. So essentially what you reduce the problem with this decomposition is that you are dealing with a quantum field theory in a curved background. If you adopt this, then you can go through all the steps that we had in the previous slide, and your equation governing the scale of gamma takes the same form as we had it before. The only difference is that now we are dealing with more fields. So if you have a gauge fixing term, then you also have ghosts, and these add to the fields that contribute to the right-hand side. Now, it's also essential to have this background field to define the Gauss-Kreinig scale. But in the end, you reach the point where you have integrated out all fluctuations, and then it doesn't matter how you organize them. So you can expect that your endpoint of the RG flow is actually independent on how you chose G bar. Now, this is the word of warning. So if you want to extract physics from this construction, do not do so at finite scale. Just go to the very end, compute the quantum effective action, and let this object determine your physics. And if you do so, then you avoid a lot of confusion that has been discussed in the last couple of years. Now we have the setup. We also want to actually be able to draw information from this equation, and then we have to resort to approximations. What is commonly done is to actually project the content of the equation to a subset of all the interaction monomials that are available. So you equip these monomials with k-dependent coupling constants. You substitute such an ansatz into your flow equation. You throw everything away that is not on the subspace spanned by your OIs. And on this subset, you compare left-hand side and right-hand side to get the information how your U bar changes if you integrate out fluctuations. Now, there are two projection schemes that have been commonly used in these explorations. So you can project on background structures. So that means you solve the equation at fluctuation field equals to 0. Or you can also project on correlation functions for the fluctuation fields. So for example, in this way, you could get information about the graviton two-point function by checking how the second functional derivative of gamma changes with the scale k. So for the purpose of the talk, I will limit myself to just the background structure. It's just to keep in mind that the community has gone beyond these computations and also looked into this technical setup. Now let's go to the practical example, how to make this equation and put it to use. So this is a glimpse on the elements that can actually appear in the gravitational part of the effective action. So there's a lot of them. And in the simplest case, you would reduce the subspace of terms to be retained just to be the one that you have in the Einstein-Hilbert action. Then the approximation of gamma k reads as follows. So you have the Einstein-Hilbert action. You equip it with a gauge fixing term. This comes with a ghost term. And this ansatz, by definition, retains two couplings that are allowed to depend on scale. So this is the Newton's coupling and the cosmological constant. You convert these guys into dimensionless quantities for convenience by scaling with the coarse-graining scale. And then you plug it into your equations, use the early time heat kernel expansion to compute the trace. And you can do so very explicitly, getting the dynamical equations that determine the scale dependence of G and lambda. So they are written here. They still fit onto one slide in this talk. Now, having these equations, you would be interested in knowing if they permit fixed points. Fixed points are the points where the right-hand side of these equations vanishes, identical, and then you find that there are actually two fixed point solutions. So there's the Gaussian fixed point, where both the dimensionless Newton's coupling and the cosmological constant vanish. You find that this is Fourier repulsive for G. This is important. So if you start with a theory where this G is greater than 0, it will not go to this Gaussian fixed point. Means you cannot use this Gaussian fixed point as a UV completion for your gravitational theory. But there's also a non-Gaussian fixed point solution. So this is at positive G, positive lambda, and this attracts the flow in all directions that we probe in this approximation. So this is shown here in the phase space diagram. Up here, we have the non-Gaussian fixed point. Down here, we have the Gaussian fixed point. Arrows, again, point from high to low energy. Our world lives essentially here somewhere. And if we trace it back under the inverse RG flow, we see it's not coming from the Gaussian fixed point, the free theory. It comes from this non-Gaussian one. Now, this is related to...
I see one more question.
Yes.
Can I ask another question about this parameter k?
Yes.
Is it a 3-vector or a 4-vector?
4-vector.
And k squared could be positive, negative, or 0?
We are, at this part of the talk, we are Euclidean, so it can only be positive or 0.
Okay, but in Minkowski, do you know that it only responds to on or inside the light code?
So this is touching a very interesting discussion. So RG equations of the form that we discussed canonically only work in Euclidean signature. So to extend them really to a Lorentzian signature computation is an open problem where we just started with.
Oh, okay.
And how to do this is not yet very clear. Okay,
so your original comment about trying to implement causality is completely unaddressed yet.
If I have time, I will comment on this in part 2. But in terms of first principle computations, they are all at the level of Euclidean computations, with, I think, one exception where you do a big rotation in terms of continuation to Lorentzian space.
Okay.
But our knowledge about Lorentzian structures is very limited. Then this question here is tailored to Sravan's comment. So are G-flows and setting the scale. So in principle, what I've done is I've converted this diagram back into dimension full units. So I reverted to scaling of small g and small lambda and restored the cosmological constant and the Newton's constant in dimension full units. And what we then find is essentially two scaling regimes. So at very high energies, we see that the things undergo fixed point scaling. So the line here just tells us that the dimensionless quantities are constant. And this fall off also tells us that dimensionless Newton's constant stayed constant. But then we see that there is crossover, and at some point, the dimension-full coupling constants freeze out and they become constant. And you can assign the scale where this freeze out happens precisely to the Planck scale. And then you would see that the construction actually generates the Planck scale dynamically. So from a scale-free theory at the fixed point, you go away from this fixed point, and then you generate the scale associated with the Planck scale. And you can also accommodate a realistic value of the cosmological constant. So here we specifically picked one solution in this diagram where the cosmological constant is very small and positive. So that would be a candidate theory for a theory connected to what we observe in nature.
Sorry, Frank, can I ask you a question?
Sure.
So is the behavior of these two curves gauge dependent?
No.
Okay.
So the characteristic features that you have two scaling regimes is robust against everything that you can do to the theory.
Mm-hmm.
Can you tell us why lambda started off positive?
Lambda starts off positive?
Yes, I mean, you've run it down and it stayed positive, but why did it start positive?
This is the position of the fixed point that you have here. It turns out to be positive.
Okay, thank you.
But I can also get something that starts out positive and goes negative. So essentially, I can tune the height of the plateau here as a free parameter. I can also decide it should be 0. So this is all entailed in here. Let's take a brief look at what has been done beyond that. What can we do beyond this example? So here we only tracked 2 coupling constants. Clearly, people have gone way beyond this. So we have confirmed that the fixed point that we have here actually exists in a wide range of approximations. And then one can also ask about how many free parameters are there, and there's a low number. Now one can also add matter fields, and then one finds that the asymptotic safety construction actually holds for many, but not all of the systems. It works for the standard model. It works for selected physics beyond the standard model. So adding another scalar particle for a dark matter field, this is certainly positive. And what is very interesting is that actually one could derive predictions for standard model parameters. So there's one prototypical example related to the Higgs mass. but the systematics of what can actually be predicted, so this is yet unknown. We know that there's a mechanism that allows to do these predictions, but for the full standard model, this has certainly not been worked out. Now, I would like to go to the last part of the talk, saying asymptotic safety, and we want to go beyond the derivative expansion. Now, the title of the section is actually a misnomer. It should better read Form Factors in Quantum Gravity, a Unifying Framework, because this is actually the arena where I see a lot of common ground between various quantum gravity programs. So in principle, the form factors are very interesting because they are in the center and they allow us to connect to various branches. So we can get them from first principle computations. We can use them to analyze singularity resolution, their effect in particle scattering. So this can also all be derived from these objects. Now, let's approach the problem from the perspective of asymptotic safety. So we argued what we are interested in is the number of free parameters. We would like to know if the low energy physics is compatible with observations. We would like to know what are the degrees of freedom of our theory. And we would like to know if it's unitary. So as a wish list. Then we build on the derivative expansion. And then you notice this has limited power if you want to address the last two questions. So you can, if you have unitarity and you want to check it with a derivative expansion, this fails by construction. Now the question that was in the room is, can we do better? And the idea is we start from the derivative expansion, and instead of working with these towers of derivatives, we condense them into free functions. So in this way, you introduce form factors in the gravitational sector. So they are allowed to be functions of our space-time derivatives. Now, it turns out that once you take the step from a derivative expansion to a curvature expansion, then you can actually address the questions about the degrees of freedom in a meaningful way. But you have to do this transition. Now, at this point, I can also make the transition from Euclidean to Lorentzian and discuss the real physics in the sense. So if we look at the structure of gravity, then at the level of two derivative terms, we can actually write down two of these free functions. Everything else is redundant, so you have the freedom of these two functions. So in principle, you should see these free functions as the objects which generalize the energy dependence of coupling constants that we observe in experiments. So you can replace mentally the delta here by the center of mass energy, and then you would see that the corresponding coupling constants will develop an energy dependence. If we have the two functions here, then we have completely fixed the graviton propagator in flat space. Also, there's a remark. So since we are dealing with an effective action here and a massless field theory, then we should expect that these functions can contain non-local terms. Now, if we adopt this framework, we can use it to embed various theories of gravity essentially in a unifying framework. So if we take classical stellar gravity, we would set these functions to constant. Then we are at a quadratic gravity C. If we do an effective field theory computations, then these functions would be logarithms of the Laplacian. And if we want to work with non-local ghost-free gravity, then they will be exponential functions. So in this way, we have a nice unifying framework in which we can study all these theories in one stroke. Now there are also some phenomenological applications, so you can use them to mimic the effect of a cosmological constant or mass term for gravitational fluctuations. Now we do a specific example in terms of scattering. So we want to have a phi goes to chi scattering process in flat Minkowski space. There are two contributions, so gravity-mediated one and scalar self-interactions. We can classify all the terms that can contribute to such a process at the level of the effective action. So the building blocks involve the definition of the gravitational propagators. So this is the gravitational part. We need to equip this with a gauge fixing term. So here we have two gauge fixing parameters as free parameters. This is a cross-check that at the end of the computation, nothing should depend on alpha and beta. So in the end, they should drop out if everything works out correctly. Then we have the dynamics of the scalar fields and their interactions with the gravity that can contribute to a three-point vertex involving one graviton and two scalars. And we have scalar self-interactions. And this is everything that you can write down for such an amplitude at the level of a quantum field theory. Now, you can derive the corresponding amplitude, evaluating the corresponding Feynman diagrams. This is what you get out of it. So it depends on your propagators for the graviton fluctuations, the scalar graviton fluctuations, and your four factors evaluated on shell. Cross-check. We check that this is explicitly gauge invariant. So whatever you did in terms of the gauge fixing term, it's dropped out. It's invariant under rescaling of your graviton. And it's the most general amplitude that you can write down for this type of scattering processes. Now we can exemplify this and look at stellar gravity. So here, this is particularly simple. So we have the functions W being constants, and we take the scalars to be minimally coupled. Then we can substitute this into the general amplitude, and we can extract partial wave amplitudes to extract this dependence on the scattering angle. This is the pictorial result. So the straight line is what we have in general relativity, and the peak is the one that we find for stellar gravity. So what we see is that for very high center of mass energies, stellar gravity goes to a constant. And this is done by having this additional degree of freedom associated to the ghost mode sitting in here. So the ghost really tames the UV divergence of the amplitude and drives it to a constant. Now I can do the similar analysis for all types of form factors that you can find in the literature. So exponential ones, constant ones, effective field theory ones, and you can study the behavior of the corresponding amplitudes. So in this way, you really achieve a unifying framework in which we can address such questions in a unifying way. Now we would like to have a set of form factors that actually implements the idea of asymptotic safety, also in a Lorentzian setting, just as a proof of principle that it can be done. Now, what would we like to have is we want to have that the amplitude becomes scale-free and constant at high energy. It should not introduce new massive degrees of freedom, like we saw in stellar gravity, and it should be local at high energy. And then, well, you sit at home, you are confined to Corona, and then you think about a model that actually does the job. So we really found form factors that meet all these requirements. So they are written down here. So we replace the function W by tangent hyperbolic, and we also needed a scalar self-interaction in order to be able to remove all the divergences from all scattering channels. Now, this satisfies all the requirements that we had, but it requires relations between propagators and vertices. And it turns out the model is not unique. We also don't have a first principle derivation of it. And in principle, it's short if you look at S-matrix theory and analytic behavior that you want to have for scattering amplitudes. So this is not entirely implemented in this framework. But as a proof of principle, it works. So you can substitute these into your partial wave amplitudes. And then you see you get the taming of the amplitude without introducing the resonances that we saw in terms of stellar gravity. So the amplitude is scale-free at scales GS much larger than 1. Now, you want to have this at all possible scattering channels, so also the cross process should be finite. Then you encounter that there is an additional problem, namely the amplitude in the cross channel will diverge unless you have scalar self-interactions sitting around. But you can introduce them, and then you get something that is finite in terms of amplitudes in all possible scattering channels. Now, how is this done? One should look at the analytic structure of the propagator that we wrote down. And then we found that it has an infinite number of poles in the complex momentum plane in such a way that you have a massless particle, and all the other poles appear as precisely imaginary momenta. So this makes the model different from what you have in typically weak models, where you would have poles in the complex momentum plane as a positive mass. Now one should relate this to what has been done at the level of first principle computations. So there have been various attempts to actually compute form factors by solving the corresponding flow equations. There's a mounting literature on that. The required relations between propagators and vertices have been observed in various instances. So they really are related to the fact that you have a fixed point governing the UV behavior. And then on this basis, you can also understand why RG improvements fail to reproduce all amplitudes. So this is a discussion that has been evoked in the literature. In principle, you see that the scattering amplitude contains two free functions for form factors and form factors for interactions, which have quite complicated momentum dependence. And trying to derive this structure from a single coupling constant that depends on energy scale should not work. So essentially, the freedom that you have in a scale-dependent coupling constant is not sufficient to describe your amplitudes. So this is understood that these RG improvements can only work in very special cases. Now, let me spend 1 minute about outlook and a vision in terms of the new standard model of particle physics. So in principle, we know that the standard model of particle physics works very well in terms of evaluations. It certainly works at the energy scales of the LHC, but we also know that if we extrapolate the model to the Planck scale and beyond, then we run into problems, Landau poles being one of them. Then we have space-time fluctuations that could play a role. And that could modify the theory. And we see that in this regime, the UV completion could actually add predictive power to the construction. So it's very tempting to say we should try to construct an extension of the standard model of particle physics that only contains the graviton as a particular or new degree of freedom. And I think it's a good question to ask whether such a theory can successfully construct it on the theory space that is common to our programs. So this brings me to the end of the talk, and I thank you for the attention.
Okay, thank you very much, Frank, for your very interesting talk, a very nice presentation. We can expect many questions. Okay, Esposita, Gianpietro, please ask your question.
I would like to know your opinion on the following topic. The opponents of the program say that for cosmological applications, one assumes the existence of an infinitive point, which on the other hand is not true at all even in simple theory. So the enigmatic existence of an infrared fixed point, which has been assumed in cosmological applications, is regarded as a weak point by the opponents. What's your view about this?
Well, in principle, the construction definitely has room for an infrared fixed point. In principle, what we have in terms of the example that we see in the phase space, let me go back to the first section. So the fixed point that we have seen in this diagram is certainly a saddle point. So you could use this fixed point as an infrared fixed point if you approach it from a different direction. So on the technical side, there is room to realize such an infrared fixed point for a cosmological model. But then you have to make sure that it is actually giving you the phenomenology that you want to see to describe cosmology. And that might be the tricky part of the program. So in principle, you inherit a scale dependence of G and lambda from such an infrared fixed point. And this could be actually give you severe constraints on possible observations.
Thank you.
Okay. I see one more question. A question from Anna Tokareva. Anna, please ask your question.
Hello, everyone. Do you hear me?
Yes, perfectly.
Great. Thank you very much for your interesting talk. I had a question regarding the amplitudes and the requirements on amplitudes following from asymptotic safety assumption.
Yes.
Do you assume that the amplitude should go to the constant when S parameter is going to infinity, and
yes.
T parameter is of order of S parameter in this regime?
Yes.
Then I have a question about analyticity requirements. Do you require the same properties for all complex values of S and T, or you don't care about this? You have nothing to say about this?
I have nothing to say about the extension to complex momenta at the moment. Apart from that, I expect that the true amplitude and the true S matrix should have branch cuts, which are not incorporated in the model.
The branch cuts normally are along the real axis. Do you expect some other branch cuts?
No, but at the moment, there are no cuts in these types of propagators.
Yeah, you have tower complex imaginary poles here.
Yes.
Then I had a question: why you say that just imaginary poles are better than those with the real parts?
If you talk about standardly weak theories, then there was a long discussion about can they be causal. And I think my understanding of the subject is if you have these, then you will inherit some violation of causality at microscopic scales. And it's my understanding that these imaginary poles essentially avoid this conclusion.
Okay.
So therefore, I like the imaginary poles better than one with a complex momentum.
Is there any arguments why it happened? Why it's still causal theory?
In principle, you can treat the G2. So you can interpret the specific form factors that you introduced here, and you can remove them by a field redefinition. So they are invertible for all real momenta, and that would be the condition that you need. And then you could shift them into the interactions. Your amplitude will stay invariant under such a redefinition, but in the end, your theory will then just have a standard propagator of a massless field, and then you should be good.
I see. Okay. I think that's something to be still verified. The question of causality.
Yes.
Is,
yes.
Even in the case of there is just an essential singularity, which happens in non-local theories.
Yes.
There are a lot of complaints about causality.
Yes, but I think this is something that we definitely should pool forces to get insights on what is acceptable and what not.
Okay, I see. And regarding the behavior of amplitudes with momenta, do you have something about the forward limit of amplitudes?
The forward limit. So there you have the typical kinematical poles, but otherwise the amplitude is good.
Yeah, you have the poles, and the UV behavior should also be kind of specific, at least in a local series. But if you don't have any boundedness properties of the amplitudes on the complex plane, which probably means that you are not requiring locality. I mean, if you require locality, then you are very constrained of what should happen, especially in the forward limit with the amplitude. And I wonder if it's even possible to have asymptotic safety together with locality.
Okay, I think this is something that I have to look into detail. What precisely can be learned into the forward amplitude? But in principle, the way we did this construction is we checked that all amplitudes for all values of t are actually well behaved in the high energy limit.
Yes, I agree that it would be the same, but then kind of the behavior, the assumptions about how all that behaves for complex momenta will bring some new constraints.
Yes, but in principle, the nice feature of this model is that you have control about everything at the level of the toy model. So you can ask any specific question that you would like to answer.
Yeah, but here I need to do something with complex values of momenta to match this to some known studies implementation of dispersion relations for amplitudes, but all they are rely on locality.
Yes.
And
but in principle, you can check it.
Yeah, I understand. So, probably it's an interesting direction too. Okay, thank you.
Okay, I see some questions. I see a question from Alexei Koshelev. Alexei, please ask your question.
Yes, thank you very much. And thanks, Frank, for a great talk. Actually, I have a question more or less related to what Anna has asked, but I would mainly ask you about the form factor of tangent hyperbolic, which, honestly speaking, I don't understand. since I spent quite a bit of time on this theory, I would be happy to understand, because it doesn't reduce to any exponent of entire function. You will have a bunch of complex poles, which are imaginary, as you correctly mentioned, as long as you're around Minkowski space, I guess. Once you go to something more weird, they will not be even complex conjugate. What should I do with all of that otherwise? It will bring me, I was all time believe that unless I put exponent of entire function somewhere in front of propagator to really mathematically avoid extra poles, I would not be able to do much. I mean, as long as I go to quantum questions like scattering or whatever, quantization, to which you, I suppose, want to go. So I want to understand, how do you plan to work with this tangent hyperbolic, especially if you go to non-Minkowski background, or if you want to expand around a given background and not around a vacuum. How will all this work?
So in principle, the expansion to other backgrounds works because we formulated all these form factors in a covariant way. So no, in principle, you have
but if it will be, for example, you take a black hole background, the corresponding poles, will they remain complex conjugate for at least? I even don't say imaginary, truly imaginary. Will they remain complex conjugate in Lorentzian signature when you will apply all of that?
So in flat space, yes. For black hole space times, we didn't check. But I take this as a very interesting question, I must say.
Yes, because I'm not sure I understand how this mathematically will work. Even though I believe I have spent some time, I'm not sure. I'm not sure I understand. If you go up beyond, if you go beyond maximally symmetric space times, let's say like this, I'm not sure I understand how this kind of construction will work. So if you have something to comment on this, I would be happy to understand.
At this stage, I have to say, I cannot add something constructive. So I think your insights on these models are far beyond what I understand. So take this as a toy model, which is the basis of discussion. And I'm happy to learn about limitations of this model in order to better understand what we should get from first principle computations.
Yeah,
so I think that
maybe we can discuss this deeper afterward, somewhat more private environment. But this is indeed tricky thing, because I understand what you did for the real axis, and this is great, but and this is very much related to what Anna had asked, because behavior on the complex plane also looks like important for many questions.
I agree.
Okay, thank you very much.
Okay, I see also questions from Philip. Philip, please ask your question.
Well, first of all, thank you for the presentation. In regard to Anna's question a moment ago, when you said the high energy behavior is under control, what you mean is, in the language of dispersion theory, you know how many subtractions a scattering amplitude might need. But the real question is, if you have a branch point, which you must have a branch cut along the real axis, then you need to know the discontinuity across it, and you need to know that it's positive. And I think that's the unitarity question. It's not enough to know that it's well behaved at very large values of the Mandelstam variables, because that's only telling you about the subtractions in the dispersion relation, but not about the discontinuity. And I think that may have been what Anna was concerned about.
Okay. It might be that the bounded of the amplitude is necessary but not sufficient.
Yes, that's what dispersion theory
is
telling us. Yes.
Yes.
Now, the other comment, which is a very general one, once you're going to incorporate non-local interactions why would you ever care about renormalizable field theory to begin with? I mean, why should we do this for gravity and not do it for QED? I mean, you know, at what point do we say that we should throw renormalizability out the window?
Well, in principle, we would like to have this to gain predictive power. So if you are happy with an effective field theory description of gravity, where there's this statement that you add just all possible counter terms and determine all the coefficients, that will certainly work as well. The question is, can you do better?
Well,
and at which price?
No, I mean, I don't want to spend time discussing my own work. I mean, the one example that you did not include right at the beginning in your map of all of the possible quantum gravity theories was one based on pure fourth order.
Yes, the c squared.
Yes, c squared on its own. You're always discussing a theory where you start with Einstein-Hilbert and ask what you have to do to improve it. But the approach that I've taken, and I've been working on this a while, is just stay with pure c squared. Carl Bender and I have shown that there's no ghost. It's renormalizable, it's unitary, and it's fine. So that's, if you ask me what I would do, I would have said, let me try to make gravity look as much like QED as possible. But if you want to say no, let me make gravity look different from QED, then I have to ask you, why do you want QED to look like QED? That's my question. Well, once you do what you're doing, which is fine, I mean, I understand all that, and it's much more than I could have hoped to do for myself. But once you do that, then the whole question of why did we ever like renormalizable field theories in the first place?
I think with your comment, I have to apologize. In principle, your c-squared theory should be on the list of that I had in the beginning of inhabitants of theory space. It should be here.
It's fine. It's okay. I think you had a graph even earlier.
Yeah.
But that's okay. Thank you for that.
Okay.
You understand my concern
yes.
about the whole general idea. I mean, we've learned so much about QED and about SU2 cross U1 and about QCD.
Yes.
Because they are renormalizable.
Yes.
So it seems odd that if we're going to do something very sophisticated with gravity, why we should not then be doing that to SU2 cross U1 cross SU3. That's what I find puzzling.
I think for QCD, we know that it works. I think
yes, I understand that. Yes.
And I think at some point I had this complete wish list here. And maybe this is a good point of discussion. So if I replace this one by c-squared theory, then can I pass everything that is on points 3 and 4?
Yes, the answer is yes, as far as I've gone. Basically, the trivial statement is the following. If a theory is based on the square of the Ricci tensor, then Ricci flat is an exact solution.
Yes.
So Schwarzschild is an exact solution to fourth order gravity.
Yes, I learned this painfully.
Yes, however, there are other solutions and they change when you go to distances. So the question is, can you use those solutions and not have to introduce dark matter? And that's exactly what I've done. In other words, when you talk about the tests of general relativity, when everybody does this, what you mean is, gravitational bending of light, perihelion of Mercury, and so on. That's fine. But then you say, but when we get to galaxies, we'll have to throw in dark matter, and we'll regard that as further evidence for relativity. And I would say, no, I would say that's evidence that it didn't work. I mean, that's the viewpoint that I've been pushing. And then when you go to dark energy, it's the same story again. You should have a lambda of order 10 to the 60, not an lambda of 0.7. And then you say, well, I'll make it 0.7 and then it works. So you see, the term tests of general relativity has a little bit of a bias in it.
Yes.
That's all I meant. Now, of course, you're absolutely correct. And I've still, I mean, if I want to work in any theory of gravity, I've still got to recover everything. I understand that. And I'm going as fast as I can.
But then I think this is something that we should figure out in how to use the points 3 and 4 in order to discriminate between the starting points that we had on the list here. So clearly I can extend this list by a few more, and I would really like to know specifically if observations can be used to rule out such a starting point.
Well, let me say this. I don't want to give a lecture, but basically you have to ask the following question. We like Newtonian gravity and we like Einstein gravity,
yes,
because you introduce the known sources and you predict the geometry. So the known sources are the luminous ones. So the challenge when you go to cosmology and to galaxies is knowing the luminous distribution alone, can you fix the orbits? And that's what those of us in alternate gravity, that's what we do. We predict the orbits from the luminous distribution alone. Now, that seems to me, if you like Newtonian gravity, then you like the idea that knowing the luminous sources tells you the orbits. So what I think you have to start with is aim for theories for which a knowledge of the luminous sources alone will give you a prediction as to the dynamics. Now, lambda CDM is not excluded. I mean, to me, it's always bothered me. You use CDM in order to produce the galaxies, but then you don't know which galactic halo goes with which luminous distribution. And that's why that's where lambda CDM is stuck at the moment. So if you could resolve that problem, if you could say, I know that in galaxy formation, if I get a particular kind of galactic dark matter halo, I'm going to get a very specific luminous distribution. Then I think that would be the road to develop this theory. I think if you want to come in from the phenomenology, the phenomenology has this big shortcoming in that you don't know how to connect halos to distributions, and you don't know how to control the cosmological constant. I think that it seems that it's a two-pronged approach. You've got to tackle those questions, but you've also got to tackle the fundamental question. Now, your program is really concerned with the behavior of gravity far off the mass shell, whereas the phenomenology is gravity on the mass shell. And we don't seem to have a link between those two things. I mean, string theory has been worked on for many years, and string theory is a very brave attempt to discuss gravity far off the mass shell, but not a particularly good effort so far to describe gravity on the mass shell. I mean, what you'd like above anything is that string theory would naturally lead you to omega lambda is 0.7. But that's not happened yet.
No.
So I think what you're doing is you're solving you're attacking the short distance behavior of gravity theories that are based on the Einstein-Hilbert action. But on the other hand, the phenomenology is sort of downstream. And I think what you were trying to say was maybe in trying to focus on theories, you should have more phenomenological input. That's basically what I was saying.
Yes, but with the more phenomenological input, and thinking outside of the box, there we are definitely on the same page.
All right, thank you.
Okay, I see one more question. The questions comes from Shravan. Shravan, please ask your question.
Hi, Frank. Thanks for the very nice talk. Actually, kind of in the same spirit but in the context of early universe cosmology, I think any quantum gravity theory needs some kind of evidence from early universe cosmology. I mean, that's the only hope for either CMB or primordial gravitational waves. I'm just wondering if there is any kind of progress or some ideas which are developed in the asymptotic safety program. I would like to know your opinion. How can we perhaps eventually go for testing asymptotic safety ideas with the early universe cosmology? I'm curious to know your opinion on the comments about this.
Well, there was this recent work about quantum gravity predictions for primordial gravitational waves by, I think it was, okay, I would have to look it up on my desk. But in principle, the idea of building these predictions on a scale-free theory would be very much in line in what you expect in asymptotic safety, since there the fixed point would naturally give you something that is scale-free. So maybe one could make a connection on that line.
Okay. Okay. More questions, please? I don't see more questions. If there is no more questions, let's thank Frank once again for his very interesting talk. Thank you very much.
Thank you very much, Frank.
Thank you for staying.
Thank you very much.
Thank you very much.
Good night.
Thank you. Bye-bye.
Thank you very much.
Frank, maybe
Thank
if you can send us the slides, we can upload it in the website.
Yes, I can send it to you, definitely.
Frank, before you leave us, can you tell us where your university is?
It's Nijmegen.
Oh, okay. Yes. That's in the Netherlands.
It's in the Netherlands, but not in Holland.
Not in Holland.
No, Holland are two states. Like it would be saying, like the US is Washington, D.C.
Oh, I see. Okay.
And typically...
I'm sorry, I'm English, and we grew up knowing its name as Holland.
Mm-hmm. No, the Dutch are very sensitive about Holland and the Netherlands discriminating between the two.
Okay.
Because the Holland provinces, that are the rich ones.
Oh. Okay. But anyway, whatever it is, you're in Nijmegen.
Yes.
Yeah, thank you.
Okay.
Okay.
Okay. Thank you very much, Frank.
Thank you.
Thank you. Bye-bye.